Okay, in this video we're going to be looking at applications of differentiation with your logs and exponentials. I think you just need to realize that you just have to do pretty much what you did in the last test, okay? And you're just going to be doing it with different functions. There is some information about e to the x here, and if you haven't come across in questions so far, I guess it's good to point it out now. When we talk about these sort of things here, this sign means approaches. I love it when it does that. Okay, where were we? Sorry, guys, just hang on a sec. Yeah. So when we talk about this here, we're actually talking about approaching, okay? Because sometimes you're not going to get a value. So when you see this, it says x, as x approaches infinite, so as x gets really large, y, which is the values on this graph, you could actually see if you look at the graph here, as x is going this way, the y values are just getting enormous, okay? They're getting larger and larger and larger. So we just need to say y is getting really, really big as well, okay? And there's some other descriptors here. Since dy by dx is the same as e to the x, and as x approaches infinity, then the slope will also approach infinity as well. Another point too is as x approaches negative infinity, okay, you'll find that y is getting closer to 0, right? So you see it here, okay? So you just need to realize that language is sometimes in questions. So you can either look at the graph, you can do them algebraically, which I might show you a bit later, but you do have questions like that. All right, there's all your rules. And also for applications, you'll see tangents, stationary, horizontal. Yes, the person that did that's done a fantastic job of organizing all those notes. And we'll just start with this example here. All right, so we just got a function and it just says find the x and y intercepts, okay? So x-intercepts where the other is 0, okay? So if I let y equal 0, I'll get 2, 0 equal to that. Maybe put the e to the minus x on the other side. And then you can rewrite it as a logarithm. So you can just say that minus x equals ln2, x equals minus ln2, okay? To find the y-intercept, that's when x equals 0. Basically, you'll get y is equal to 2, take away e to the minus 0, and that's just 0. 2 take 1, so you get y equals 1. Okay, so your y-intercept is going to be 0, 1. Okay, and I didn't finish this one here. Your x-intercept is going to be minus ln2, 0. Okay. Next question, show algebraically that the function is increasing for all x. So if you haven't seen this question before, I guess you need to just realize that with this scene that y dash, the derivative is positive, okay? So that's all you need to show. So if you look at the original function, you've got 2 minus e to the minus x. If we just find dy by dx, the first one's a constant, you've got negative 1 times minus x times by negative 1 again. So it becomes positive 1 e to the minus x, okay? And I hope you guys understand. I mean, that's all you really need to do. And then you can say as dy by dx is positive, it's increasing for all x. Okay, a fancy word of saying for all x is x, all x is that. Okay. Yeah, so just to help you understand, remember that this guy here, it doesn't matter what's up the top. Okay, as long as you've got a positive number here raised to a power, that's always going to be positive. Okay, so you can see we've got a positive times a positive. So there, your final answer is that. But you don't really need any of that. These types of questions, you just need to show what the derivative was, which was that. And then you need the statement underneath going C. I know that the derivative is positive, therefore it's increasing. The next question is show that the function is concave for all x. So when we talk about concave or concave downwards, we may know that the double derivative, can't be bothered writing the other, the double derivative is negative. Okay, so if you just grab your derivative value and start with that. So in our case here, the what was it? Our derivative was 1e to the minus x. The double derivative would be minus 1e to the minus x. Pretty much just cycling around the same thing. And we do the same statement. As the double derivative is negative, it's concave for all x. Okay, so same type of thing. Show the double derivative, explain that it's negative or positive or whatever you want, and then have an explanation underneath it. Okay, use technology to do the graph. I might just leave that out for this one, and we'll just do it here. Hope you guys remember that when you do your exponentials, just to rewrite it like this to help. It's just the number at the back. Another reason a way to explain the asymptote is this thing, we knew that the e to the minus x was always positive, but another thing is that thing's never zero. So if that can never be 0, it also means that we're never going to get 0 plus 2, which is equal to 2. So like I've said to my guys in my class, whatever that number that is added or subtracted to the exponential, so what I'm trying to say is something like e to the, whatever else we've got there. This number at the back is the asymptote. Okay, so in this case here, our asymptote is just y equals 2. We've got our x-intercepts and y-intercepts. So our y-intercept was at 1. Our x-intercept, which you could find off your graph, was approximately there. It's minus ln2. Okay, and you could use the trace function or something like that to help get some key points, but that would be our graph there. Okay. Now it says explain why equal to is a horizontal asymptote. You could just use something I just said before. So like for y equals 2, take e to the minus x. We know that e to the minus x can never equal 0. In fact, it's always positive. So we're never going to get an answer of y equal to 2. Okay, and that's the way to sort of generally explain them. If you look at the solutions of the book, it explains it another way, but I think that's probably the best way to explain it now. Okay, so you can check those solutions as well if you want. Okay, next application example question is a tangent question. Okay, so it says find the equation of the tangent to y equals e to the x at the point where x equals a. So first thing we do is point of contact. So we're just going to find y given x equals a. You can use this notation if you want. So we just sub in a into the equation and you get e to the a. So the point of contact, so when x is a, y is e to the a. Let's find the slope of the tangent. To do that, we have to find dy by dx. And we know that for e to the x is exactly the same thing. So dy by dx, given that our x value is going to equal a, our slope of our tangent is going to be e to the a. All right. Now, I know that everyone does it differently, but I just sub them straight into y equals mx plus c. You just do it your own way, okay? I'm just going to sub my points in. So I've got e to the a is the y value. The slope is actually also e to the a. The x value was a, and we need to find c. So c is going to equal e to the a. Take away e to the a times a. So it's a bit of a mouthful there, but our equation will just be slope of the tangent times x, and then we'll just have plus e to the a, take e to the a times a. All right. Now, next one's a real toughie. All right. Hence, find the equation of the tangent to y equals e to the x from the origin. I think the actual hardest part is trying to understand what the heck the question's asking, really. So I might just do a quick sketch. When I first saw this question, I didn't know what it was asking. All right. So find the equation, and we're kind of using the previous knowledge. So we're just going to pick a point on the graph, and we'll use the letters that we use here. So we know one point on the graph is going to be a e to the a, but we know it's also going through the origin, right? So we want this tangent. Maybe it's not a good point to do, but we want this tangent that goes between here and here. All right, so what do we know about this tangent? Well, at the moment, we just know it's going through a point on the graph, and we're just going to call that a e to the a. Okay, you could have called it x e to the x. It just might be a bit confusing for that. But there is something we can do. We can do it old school. We know the slope of this tangent is actually just going to be the same as the slope between these 2 points, right? So One of those points is the origin. The other one is designated as a e to the a. So we can actually work out the slope of the tangent to just be, y2 take y1 over x2 take x1. And like I said, this is a real toughie, okay? Y2, so we're really going to have that over this, okay? And that's going to equal e to the a over a. And the funny thing about that is that slope of that tangent, we also know is going to be exactly as the point here. And you're going to look at me and go, well, what the heck is that? Well, we showed it earlier. It's up here, okay? At any point on the graph, there it is, the slope of the tangent will just be e to whatever that value is. So at this point, we also know the slope of the tangent is e to the a. So even though it's a bit confusing, we know that e to the a over a, which is, it's really average rate of change, but that is the slope of the tangent, is also equal to e to the a. And if you just rearrange that, you'll get a is equal to e to the a over e to the a, which explains that a has to be 1. Okay? So once you know that a is equal to 1, yeah, I told you it was a tough one, you then can actually just do it like a normal question. So the point of contact would be 1, comma. Now, if you sub that into the original equation, right, e to the 1 is just e to the 1, or just e. The slope of the tangent, we can use just this equation here. We know the slope is e to the a, or in this case, it's e to the 1, okay? And if you sub that into your equation, you'll get, y value is e is equal to the slope of the tangent times the x value plus c. So you really get e take away e, which is 0. So you don't actually have a y-intercept in this case. So the equation will just simply be y is equal to e to the x, where the slope is e. Yeah, so quite a challenging question, that one. And I've seen a couple like that. Yeah, very tricky, that one. Okay, next question. So we've got sort of a rates type question here. It says we've got a substance that decays. So if you don't remember decay from last year, we're sort of decreasing all the time. So it's actually going to have a concave upwards shape as well. That doesn't look concave upwards, but this is sort of like a inverse sort of exponential graph. Okay, and we're looking at finding K, all right, given that the weight is 10 grams after 50 hours. So 50 hours is actually the T value and W is the 10. Okay, so we're just going to sub them in the appropriate places. So W is 10 and we know that T is 50. So I'm going to have 20 E to the minus K times 50. All right. And a lot of you might want to just take the log of both sides straight away. Don't take the log of both sides until you've got E equal to stuff, okay, right? So at the moment, there's a constant out the front, right? So just realize when you're doing these questions, do not take the log unless you've just got E to something, okay? So let's just divide both sides by 20 first, okay? And you'll get a half is equal to e to the 50 minus 50 times k. Just trying to rearrange it to make it look better. Now let's take the log of both sides. So I've got ln a half equals ln e to the minus 50k. So we know that the minus 50k will go out the front and ln e becomes 1. So it's minus 50k equals ln a half. Maybe I'll just slow down. So just remember ln e, if you look at your notes, ln e is equal to 1. Okay. All right, so once I've got that, I've got a negative there. So I might even just be a bit clever and go, look, ln a half is the same as ln2 to the minus 1, which is actually the same as minus ln2. Do you see that? Just so that we can actually get rid of the negative, and it'll just make it look a bit better. So really, k, you're going to have a negative divided by a negative, divide both sides by negative 50, and you'll just get k, the negatives cancel, and you'll get k is equal to 1 on 50 ln2. Okay, now that we know that, we can put it into our calculator and just answer some simple questions using technology. So we're just subbing t equals 0 and so forth. I think I've got it in here. Yeah, there I have. So I've got it in there. So if I just draw the function, there it is. So just doing some quick stuff. T equals 0. That's really the y-intercept. So we could just go G-solve y-intercept. So when x is 0, y is 20. Okay, so we've got 20 grams. These are values. Next one, I'll only do one more. You can do the rest yourself. G-solve. We'd press F6 to do a Y calc, and it was 24 hours, wasn't it? So the second one was 24, and we get a value of 14.3 grams. And you could just do the exact same for 1 week. Just realize 1 week is really 24 hours times 7 days, which is 1.95 grams. All right. Next question. Find algebraically how long it would take for the weight to reach 1 gram. Okay. So we know we've got this equation here. So what we're going to do is let the weight equal 1, and we're going to let that equal our equation that we've created. So we've got 1 is equal to 20 e to the minus ln2 on 50 times by t. We're going to do the same thing I said before. Do not actually take the log of both sides until you've just got e on its own. So you've got 1 on 20 is equal to e to the minus ln2 on 50t. So that's really like a constant, that thing here. All right, so just, I know it's a mouthful, but we'll just keep it out there. Now we'll take the log of both sides. So we'll have ln 1 on 20 is equal to ln e to the minus ln2 on 50. That's our constant. That will go out the front, right? And ln e will become 1. So we'll get ln 1 on 20 is equal to minus ln2t on 50. All right. And then we could just rearrange that, and we would get t. Yeah, I think I did that smart thing again where, that's like 20 to the minus, because I've got a negative there. I change, so just watch my steps. I'll just do it here because I'm running out of space. I change that to be 20 to the minus 1, right? I then move the negative 1 out the front, okay? So I just hope, yeah, and it'll just get rid of the negative there. So if you just rearrange all that, like I said, I'm running out of space, you'll get t is equal to 50 ln 20 over ln 2. All right. Next question says find the rate. Okay, so just remember when we're doing rates, we've got to be doing the derivative. Okay, so what I might do is just go back. We'll just ignore that second graph, and remember I've got y1 in as the original function, so I've got to go option F, and then so option was right next to shift, and then F2 calc, and then dy by dx, and then we just select F1 for y, and we're doing the first function, press across, and then just use the normal x following my cursor there. Okay, so that's going to graph our derivative. We can draw it. It might not be in the same spot, right? So you might have to move your graph around a little bit. Okay, so I can see if I just move it across a little bit. Oh, sorry. And the first question actually says find the rate of decay after 100 hours. So we'll press Shift, G-solve, Y calc, and we need to select the other graph, which I can't see that well. Yeah, can you see it selected it now? It's got the blue one. And then I'm going to put my Y calc in straight away. So press enter on that, and then 100. And it's out of domain. That's good. That's what I wanted. Yeah, so you just need to realize it's not working because, I've got to change my domain. So if you go and look at these questions here, right, you have to change your window to be 100 and 1,000, which is annoying. And I might just quickly prove it with one of them. So I just go Shift, View Window, and we just have to make X 1,000. Sometimes the calculator struggles with this. Draw that. And you can actually, there's our green lines. Go Shift, G-solve, Y calc. Okay, and we've got to select the second one, which is the green, changing purple. And we'll put in 100 now. Okay, and it gives us our value of negative. So the rate is negative 0.0693. Okay, and it's a rate. So what is it? It's grams per hour. Okay. And I'm not going to do the next one. I'll just put the answer down. So W-1000 is tiny. Okay. how many? I think it's got 6 zeros. There we go. 1, 2, 3, 4, 5, 6. Just realise that unless you're told otherwise, you have to write to 3 sig figs, which I know is silly, but it just means that you keep going along till you hit the first number, and then you count 3 numbers, right? So there's the first number, 1, 2, 3. Okay, so that's the rule in methods. That's what they decided to do a while back. Now, last question says, show that dW dt is proportional to the weight of the substance remaining. Okay. Proportional just simply means that let's say your original equation, W equals, let's just say it's equal to T. What we're trying to say is when you do the derivative, we want it to be exactly the same as the original with just some number out the front. Okay. And that happens with these. It's actually a very special property. Okay. If you do a bit of special, you do a bit more of that sort of stuff. Okay. So let's just go. So you got W equals a bit of a mess, but we've got 20e to the minus ln2 on 50 times t. Okay, so if you do the derivative, you do exactly the same thing. And then you have to times by the constant. Okay, so the constant up here is just minus ln2 over 50. Okay, so you just need to realize that W dash T is actually the same as your original. Okay, so it's actually the same as the original, so we'll call it W, right? So that's like W, and then we're just timesing it by this constant here. Okay, so that's what we mean, it's proportional. So proportional means that, like I said, it's exactly the same with some sort of, well, we could say dilation. Okay, there's some sort of multiplying factor there. Okay, now we're pretty much halfway through, so I'm actually don't want this video to go too long, so we're just going to call this part A, and then we'll do pretty much the rest of these application questions in part B. Okay, so I'll see you when you're up to that one. Okay, thank you.